Okay, so for today's, I decided to be a bit different, and I actually did everything in advance. So today, what I did was not really a workout. It was activity. I went out with a group of it was like my girlfriend's friends, and I'm counting it as an exercise because we played tag, but like two of them were former track athletes and they were fast. So like just I think we were doing it for like nearly an hour. So like I'm counting that as a workout because that was a workout trying to run away from specifically those two. The other few people I could go against, but like those two, they would run me down so fast. But so and I will say that does not the electron transport chain and Krebs cycle was not the primary one I was using during that exercise. But because there was a lot of stopping and going, it is one of the ones I used a lot during. How can I put this? So during Epoch, after I would stop running away for whatever reason, as I would stop my motion instantly, my work level decreases, and it's primarily going to be my Krebs cycle and my electron transport chain, which brings me back to normal, brings me back to homeostasis. They are my primary energy producers at that point. So we have the molecules we had earlier. Also, I'll try to make this one a lot faster because I realized I've been going like super long with these. So we got FADH and NADH, which we have been getting from both Krebs cycles and glycolysis. It goes to the electron transport chain, which is on the outside of the mitochondrial wall. It is, it's on the mitochondrial wall, cell membrane. So we have a low concentration of hydrogen molecules within the membrane, because it's a double-walled membrane. This is within the first membrane, and well, here is the second membrane, and there's another membrane out here, being the outer membrane of the mitochondria. We're talking about the inner membrane space and the inner mitochondrial space. So low concentration of hydrogen because we are taking the electrons from FADH and NADH and are passing them along I believe seven different molecules in the electron transport chain. That is why it's called a chain, because it's more than one molecule. And so, as it goes along this chain, we have pumps, electron pump 1, 2, and 3. So the first pump and the second pump pump out 4 hydrogen molecules from the inner membrane space into the intermembrane space. So this is what maintains the low amount of hydrogen. Oh, I'm sorry, I didn't realize. The low amount of hydrogen on this space and maintains the high amount of hydrogen in the outer space. This causes a hydrogen gradient. So it goes boom, 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 all the way down to oxygen, which is the final electron receptor, which is important because this is the use of oxygen in the body, is as well, one of the uses, but a very, very important use is as the final electron receptor in the electron transport chain. So once we establish this gradient, we now want to bring those hydrogen back in. Well, those hydrogen want to come back in naturally because things want to flow from high to low. However, we use that to our advantage. We use the natural tendency of hydrogen to flow from high to low. And another uh, thing, mm, complex machine. I don't know the word for it. I don't know the exact word I'm looking for, but another part of the membrane is called ATP synthase. So ATP synthase takes those hydrogen and allows them a path from outside of the cell into the cell. Along the way, they go along this protein structure that turns. It physically, people like in here I drew it as a clover. I always understood it best as like a water wheel, because when water wheels turn, as hydrogen flows through it, it's hitting the walls of the water wheel of ATP synthase, and it's turning it like how a watermill does. And it's turning, well, I guess you can also say a windmill, but it's turning it as it goes. And as it does this, it's turning ATP synthase. ATP synthase smashes ADP in a phosphate to create ATP. Excuse me. Excuse me. So now we have hydrogen into the cell, and we have created ATP by combining ADP and inorganic phosphate together. So now these hydrogens combine with a negative oxygen that comes off as the final receptor in the electron transport chain, combines with the negative oxygen to create H2O, or water. Oxygen plus hydrogen, water. So this is why oxygen is really important in our body to create ATP. So the next thing we're gonna talk about is how much do these produce? And it will be the last thing I talk about. FADH enters at the second pump, and it has 4 and 2, so it pumps out 6 hydrogen molecules. NADH goes in at the first pump. It does 4, 4, and 2 molecules. The third pump being a weaker pump that can pump out less. Sorry, that's just TV. That can pump out less hydrogen. So in total, NADH 10 hydrogen gets pumped out, and FADH 6 hydrogen. So it roughly equates to 4 hydrogens pumped out equals 1 ATP. So NADH per NADH molecule creates 2.5 ATPs, and per 1 FADH2 molecule it creates 1.5 ATPs. So this is really important because we created a lot of these during glycolysis and Krebs cycle. Because we created so many of them, they turn out to such large values. Because I believe off the top of my head, Krebs cycle per 1 molecule of glucose creates 6 NADHs by itself, and that's 15 molecules, which is a lot. That is a lot of molecules just from 1 molecule of glucose. Not to mention the NADH we gain from glycolysis, the FADH we also gain from Krebs per molecule of glucose, which would be 2. So all of these combine together to creating such a large amount of ATP from the electron transport chain. So I think I'm going to leave it there. It still feels really long, but yeah.